to the second part of this video series on indices. In the previous tutorial, I introduced indices and sort of motivated using some simple examples the first 3 rules for manipulating indices. In this tutorial, I want to use the second of those 3 rules to just look at 2 special cases which are really helpful to be aware of, and then I'm going to motivate the 4th and final rule with indices, and then finally I'll just do a couple of examples to show you how to use these rules and to give you confidence with using them. So let's just remind ourselves of rule number 2 that we derived in the last tutorial, which is that a to a power divided by a to a different power can be written as a to the power of index m take away index n. Now, let me imagine that I'm looking at a to the 5 divided by a to the 4. Then I have 5 lots of a on top, and on the bottom I have 4 lots of a. I can strike out 4 of these factors of a, just leaving me with 1 a on the top. Now, had I implemented rule number 2 to do this problem more rapidly, I would have found that a to the 5 divided by a to the 4 is equal to a to the 5 take away 4, which is a to the 1. And so I wouldn't call this a rule, but it's just something that's very important to know, which is a quantity to a power of 1 is itself. You can sort of think of it as the sound of one hand clapping. A multiplied by itself only one time, as it were, is just itself. Similarly, if I considered something like a to the power of 4 divided by a to the power of 4, I would have 4 lots of a on the top and 4 lots of a on the bottom. So I have 4 common factors of a on both the top and the bottom. I can strike all of those out and I'm just left with 1. Again, I could have multiplied these by 1 just to give more comfort to some viewers that when I'm striking all these common factors out, I'm just left with 1 divided by 1, which is 1. Now, had I applied rule 2 to this blindly, I would have had that a to the 4 divided by a to the 4 is a to the 4 take away 4, which is 0. And so we see, comparing the outcome of this, we have the other very useful thing, which is that any quantity raised to the power of 0, any base raised to the power of 0 is 1. And this is really more of a notational convention, I think, than anything particularly meaningful. It doesn't make any sense to say any quantity multiplied by itself 0 times is 1. That just becomes a sort of linguistic fantasy. But it's a very useful notation that we have that a base raised to the power of 0 is to be interpreted as the number 1, unity. The only exception to this would be if that base perversely was 0, because 0 raised to the power of 0 is not a defined number. Right, okay, now on to the final rule, which is to do with taking powers of powers, and I think many find this quite confusing. I certainly did when I was younger. So let's consider then a squared all cubed, and so I'm putting those brackets around a squared and I'm saying I want to cube the entire thing within the brackets. Well, a squared is a times a, and then the cube tells me to multiply this thing by itself 3 times. So I have 3 lots of this bracket of a times a. And if I just count up how many a's I have here, I have 6. And what you can see is that the result comes from multiplying these 2 indices. And so we have rule number 4, which is perhaps the hardest to remember and to sort of interpret, which is a base to a power, all raised to another power. So I'm raising the base to the power of m, raising all of that to the power of n is that base to the power of m times n. So when I raise a base to a power m to yet another power n, that's the base raised to a power which is the product of those 2 bases. Right, so maybe I can just indicate something which might help people remember this. If I go back to the previous tutorial here, do you notice how when we look at indices, a product involving the same base, as far as the indices was concerned, was a sum. A division involving the bases to a power, as far as the indices was concerned, was just a subtraction. And now what we see is that a power involving the indices involving the bases as far as the indices concerned is a product. And so in each case, as far as the indices are concerned, the calculation that's being performed is sort of 1 degree of difficulty easier. A product becomes a sum, a division becomes a subtraction, powers become products. And in fact, this idea of a level of simplification is the whole basis of logarithms, which students will meet in the higher maths in Scotland or equivalent A-level or so on in other parts of the world. And when you learn the rules of logarithms, they can be a bit mysterious, but actually they follow immediately from these rules of indices that we've just been motivating in this tutorial. So let's end then with just some examples to provide some practice. So let me use a different base just so we don't think it always has to be a. So imagine I have b to the quarter times b squared divided by b to the power of 1/2. Okay, well, I think I will do the top first. I'm multiplying the same base here to different powers. I just have to add the powers, and 2 plus 1/4 I can write as an improper fraction. 2 plus 1/4 would be 9/4. And I'm dividing that by b to the 1/2. Now I have a choice how to proceed here. I can invoke rule 2, which tells me what to do if I'm dividing quantities. It tells me that I have to subtract this index from that one. So I would have b to the 9/4 take away 1/2. Now 1/2 is 2/4, so that would be 7/4. Alternatively, I could invoke rule number 3, and I could say, well, this is really b to the 9/4 multiplied by 1 over b to the 1/2. Remember from the fractions tutorial that you're always free, and it's a very liberating thing to know. When you're dealing with fractions, you're always free to write any fraction as the numerator multiplied by 1 over the denominator. And that can be very helpful sometimes in breaking fractions into pieces that are more manageable. I'm just doing it here to show that we could have used a different approach, which is to invoke rule number 3 here, which says that if I have 1 over a base to a power, I can interpret that as that base to the negative power. And then again I have a product, I have to add these bases together, and 9/4 take away a half, namely 9/4 plus negative a half is just 7/4. And let's just do one more example that involves taking perhaps some powers. So let's make it something rather terrible. Let's say it's t to the power of 3 divided by t to the power of 1/2 to the power of 5. Not too bad, actually. So with things like this, it makes sense to look at the hardest part of the expression and deal with that first. And the hardest part of the expression is the thing in the denominator there. So let's just deal with that. So we have t cubed on top. On the bottom, I have t to a power all raised to another power. So rule number 4 says multiply those indices together. So I have a half times 5 is 5/2. Okay. And then I can invoke rule number 2. I've got a division going on, so I need to subtract this power from this power. And so this would give me t to the 3 take away 5/2, which is just t to the 1/2. So really not too bad. Actually, let me just do one more. If an examiner was being devious, or if you're just using maths not for exams but for real purposes, whatever those might be, for example in science or in economics or in other forms, you might come across a base raised to a negative power but in the denominator, and that might appear rather scary. So let's just look at that, and at the same time let's just throw some other symbols in to just show that we can sort of separate things out in a very neat way. So let's say we have p to the power of 2, q to the power of 1/2, divided by, let's say we have pq all raised to the power of -2. Now this might be terrifying because you might think, well, I don't know what to do if I have a negative power in the denominator, but actually you do know what to do. You can interpret an index in the denominator as taking that object up to the numerator and switching the sign of the index. So this is p squared q to the 1/2 times, I'm taking this upstairs now, pq, and I'm switching the sign of the index. And now I just need to deal with these indices, but I have to treat each base separately, very important. So this pq all squared is p squared times q squared. So I have a p squared times a p squared gives me p to the 4th. And then I have a q squared times q to the 1/2. So I just invoke rule number 1. I just add those indices together, and 2 plus 1/2 would be 5/2. So a slightly, ugly example to finish, but really these are designed to show you that if you use these rules of indices systematically, often there's more than one way that you can go about it, and you should find your way pretty smartly to the answer. So I hope these 2 tutorials on indices have been helpful. I think students often find this a tricky topic. I hope that motivating the rules using some simple examples has been helpful in giving you faith in the rules, and in fact you'd even be able to rederive them for yourselves if you needed to, just using these simple examples. So hope that's helpful, and I'll see you next time.